Hey, what's up, guys? Okay, so this video, welcome to my analytic number theory. So, in this video, let me just introduce the asymptotics. Okay, so estimate. So this video just talking about the simple small big O notation, and also quickly tell you that the idea of the how to bound these, how to use the very simple idea to bound these arithmetic functions. Okay, so the key, usually there are two steps, the two kind of function, right? So basically, our idea is that somebody gives you an analytic function, and you need to bound the first kind of term is to bound this, and the second type of term is to bound this, right? So basically, you just do the average. Okay, so there are some famous results that in the future that we will approve. Okay. Okay. Like prime number theorem, right? So one famous result is the prime number theorem. If you calculate Wegener function, then it becomes approximate to x. Right? This is the prime number theorem. Okay. Okay, and then let me just quickly introduce the standard notations. Okay, so there are big O is small o. So let me just first one is that when I write f equals to big O g of x, means that there is a constant x0s and c, such that f of x is equal to c g of x for every x greater than x0. Okay, so basically basically when x is large enough, your f of x will bounded by c times g of x. Okay. The second is the small o. Basically means that if there's x0s and c, and sorry, you don't need this for small o. When I write f equal to small g of x, that means that g of x is dominate f of x. So then this means this goes to 0 as x goes to infinity. Okay. And by the way, g of x should not be 0 for sufficiently large x. Ooh, okay. The third notation that some people will write this. Okay, so this just tell you that g of x is non-zero for sufficient x large, and the limit f divided by g will be 1. Okay, let me just the first. Basically, this is a very famous notation called Vinogradov's notation. If you see Terry Tao's video or the analytic number theory video lecture, that people always use this strange notation called f of x, right, as this. Okay, so this means that f of x is just big O g of x, right? But some people in the analytic number theory, people like to use this notation. Okay, there are fifth notation called the order estimate. So order estimate. This notation means that usually people write as this. Okay, so this means what? This means what? Means that there are approximation order, or basically it means that f of x, this guy, less or equal very less g of x very less to f of x. Okay, so both means that they are the same order. Okay. Or equivalently means that there exists x0s and the c1 and c2, such that f of x is bounded by c2 g of x and greater or equal to c1 g of x. Okay, for all x greater than x0. Okay, so this is the common notation that we will encounter. Okay. Okay, so sometimes that we will have some other results, right? But okay, so the sixth notation, I think this is also important, called the dependence of parameters. Okay, so this means that if your f and g contain some parameter lambda, then some people will write f of x, O of lambda g of x. So this means that they depend on lambda, and maybe for particular lambda region, right? So usually this will be some specified lambda region. Okay. I think once you know this, then this is enough. Okay. So let's talk about the standard example. For example, if the power law is less than equal to the exponential, right? So you can write this exponential cx, right, for each alpha and c, right? This is the standard notation. So for every c equals 0. Okay, and the exponential alpha. Okay, so exponential alpha will approximate the same order back of magnitude with this, right? For if alpha less than 1. Okay, you can check for these kind of things. And also log x is O of epsilon x epsilon, right? So this means because log x is less or equal to x to any power, right? For any epsilon greater than 0. These are all very classical results. That you just have some better simple idea in the calculus that you can prove this. Or maybe the log 1 plus x, right? You know that this is 1 minus x, right? Plus x minus x squared divided by 2, x cubed divided by 3, keep going, right? So this is a magnitude of all of x, right? If let's say if x less or equal to half, right? Because you can bound this term converge, right? So you can bound this by some constant, right? So this order of x. Okay, and yeah, these are common results that people like to see. So I skip the proof. Okay, so let me just talking about examples from number theories. Okay, so this is for a prime number theory. So basically, you can view the prime number theory as the first triance that in the number theory that people can prove, right? So I already let me just quickly review. So pi of x defined to be all the primes less or equal to x, right? So p is a prime. Okay, and then the prime number theorem, the simple idea in the prime number theorem tell you that pi of x. Okay, so pi of x is just x plus log x, and the order is bounded by x log x squared. Okay, so this is the first version called P and T. Okay, so this is the prime number theorem. So basically, you can view that, or basically you can check this. Okay, so maybe the very simple version is this. Right, so I use the same magnitude and the bounded by 1. Okay, and this is the first fine version, that the first fine version, and then you get the second, the more finer version. Okay, the more finer version is that you define this Lix. This is the famous integral. I think it's dt log t. Let's say from 2 to x, right? So this Lix, then you can check that your pi of x is basically Lix plus, this is the more finer version. That's O of alpha x exponential minus log x, and with alpha power. Okay, and then this is true for alpha less or equal to 3 divided by 5. Okay, so this is the more finer version of the tighter bound of this prime number theory. Okay, and if you assume the Riemann hypothesis as an arch, that you can prove that the pi of x is Li of x. So this is why the arch is important, because in the Riemann hypothesis that you assume that every critical zeros is on the every zero is on the critical line with the real part half. So you can prove that. So basically, don't worry, I will prove this in the future. But half plus half. Right, so this is the more tighter bound than, because this is power, right? X, and this is time sign exponential. So this guy is not so tight as this bound, right? This bound is very tight because this is exponential, and this guy has some exponential x, but the time something, right? Okay, so this is the basic idea that I think you can check, and there are additional examples that I will post the notes for you guys to see. So there are additional examples and the various exercise and something you can check for it's true or not. It's true. Okay, and maybe in the next time, let me just say about how to bound the logarithmic integral, and give you the bound for this. Okay, so this is just see you guys next videos.